Back to part 2, right? So the main goal is to prove theorem 7.8 star, which is slightly more general than what's stated in Lucchesi-Murty, right? So it says that a matching code graph is not Birkhoff von Neumann if and only if it has a conformal or bicycle, and we are going to assume whatever we need in order to prove this, right? Whatever we need, and we have already stated. Actually, there's one thing I have not stated, but I'll state it soon, right? So what does it mean to be not Birkhoff von Neumann? Let's see what we know. We know from corollary 7.6, which is a corollary of theorem 7.5, not Birkhoff von Neumann means that the perfect matching polytope is a proper subset of the fractional polytope. Okay, we will assume this. Yeah, okay. All right. Good. So I would like to convince you that one of these two directions is easier than the other. Maybe you can think about it. Think about it for a few minutes. Which one of these directions is easier than the other? So, right? One direction says that if a graph is not Birkhoff von Neumann, then you need to show the existence of a conformal odd bicycle. The other direction says, hey, I have given you a conformal odd bicycle. Prove that the graph is not Birkhoff von Neumann. Right? Let's draw a conformal odd bicycle just to visualize. Right? So, conformal odd bicycle looks something like this. One is a 5 cycle, one is, I don't know, 3 cycle. But when I delete the vertices of Q1 and Q2, the remaining graph has a perfect matching. This is what it means to have a conformal odd bicycle. Your graph looks like this. There are more edges, I have not drawn them, but this is happening in your graph, right? And of course, this could be spanning, which is what happens in the triangular prism, in which case there is nothing here, right? But in general, it may not be spanning. Yeah? So supposing I tell you that your matching covered graph has a conformal odd bicycle, then do you see a way to prove that the perfect matching polytope is indeed a proper subset of the fractional perfect matching polytope? Right? Let's make a Venn diagram, or maybe a polytope diagram. Maybe it will serve two purposes. So maybe the perfect matching polytope looks like this. I don't know, I'm just drawing in 2D, of course. And maybe the fractional matching polytope is something like this. And the point is, because we are interested in graphs that are not Birkhoff von Neumann, in general we want this to be not empty. If you think of it as a Venn diagram. Yeah. Okay. So, yeah. Okay. Supposing which one of these is easy? Even if you don't have an answer, like a rigorous answer, just intuition is good enough. Okay? No, you're not going to use 7.8. You're going to prove 7.8 star without 7.8. That's okay. A lot of things there. Anyone else? Okay, maybe I'll give you a hint. I will tell you which one is the easier direction, and then you can tell me why it is the easier direction. So the easier direction is, I've drawn this for a reason. Right, so there is a conformal odd bicycle. Now convince yourself that the perfect matching polytope is indeed a proper subset of the fractional perfect matching polytope. To do that, you basically need to demonstrate the existence of a point here. If you show me one point here, that means that this set is non-empty and the graph is not Birkhoff onding. Right? So given a conformal odd bicycle, can you come up with a point, also known as a vector, that is going to satisfy the fractional perfect matching polytope constraints, but it should not be in the perfect matching polytope? Right? See if you can come up with such a vector for a graph that looks like this. right? So the idea is to basically give labels to all the edges, right? You can think of a vector as simply a labeling of the edges, so that the non-negativity and degree constraints hold, right? And remember that all the vertices are drawn here, right? Because this is a conformal odd bicycle, and I have drawn the perfect matching also outside the bicycle. All the vertices are here. There may be 1,000 more edges, I don't care. Right? If you care about these edges, then you actually get into trouble. The idea is to not care about those edges, to care about only these edges. Right? And you can basically just use three numbers, 0, half and 1, to create the vector. Right? And it's very similar to what you did in a prism. In the prism, we took the two odd cycles, we put half, half, half. Well, the problem in the prism is, it's a very small example. The perfect matching is empty. But in general, the perfect matching may not be empty. It may actually have edges. Right? So, you can just put a 1 on all these edges and a half on all the odd cycle edges. Do you agree? If I put a half on all the odd cycle edges, Q1 and Q2, and I put a 1 on all the M is my, this is my M. This is a perfect matching of G minus vertex set of Q1 minus vertex set of Q2. If I put a 1 on all the edges of M, and I put a 0 everywhere else, whatever edges I don't see, they are 0, then observe that this vector satisfies non-negativity and degree constraints. At every vertex, the sum is 1, and clearly it is non-negative. Yeah? And now to prove that it is not in the polytope, when you use the standard trick that we did, consider an odd cut, observe that for a certain odd cut, the sum is actually equal to 0. Take the odd cut for any odd cycle. Take partial of V of Q1. Right? If I consider the cut corresponding to this, all the edges that are going out, no matter how many they are, I put a 0 on those edges. Right? Whereas in any perfect matching, we know that X of this set will be at least 1. Edmonds constraints. So Edmonds constraints are violated for these sets, Q1 and Q2 especially. Right? So therefore this vector is not in the perfect matching polytope. So what we have done is, we have shown an element that is here, no, that is here but not here. Yeah, a point here. That means that the graph is not Birkhoff or Neumann, because we are assuming corollary 7.6. Yeah? Okay? So we are done with one direction. Any questions, concerns regarding this direction? Observe that the vector we constructed is actually half integral. By half integral, I mean it uses only 0, half and 1. Yeah? Turns out, we need something about half integrality to prove the other direction. So, we will use one more result. This will be an exercise for you. It's not difficult actually. It's very similar to something else we have already proved. And I proved it myself today. I was quite happy. So yeah, it's an exercise in Lucchesi-Murty. The result is basically the fractional perfect matching polytope is half integral, in the sense that all the extreme points of the fractional perfect matching polytope are half integral. They will only use values 0, half and 1. Let's think about the perfect matching polytope. For the perfect matching polytope, what are the extreme points? They are exactly the perfect matchings. They are integral, 0 and 1. It turns out that the fractional perfect matching polytope is half integral. That is a result, technically speaking, is a result from polyhedral combinatorics, but you can basically prove it using very graph theoretical ideas, and you will use that. So this is theorem 7.7. This is a DIY and it will be on your next assignment. Yeah, and it is actually kind of broken down into parts by Lucchesi-Murty, so it should be fairly straightforward. Okay. In fact, I would suggest try proving it without even looking at the breaking down Lucchesi-Murty. See if you can do that. And if you struggle, then you look at the parts. Okay. So it says every extreme point of the fractional perfect matching polytope is half integral. So they don't use this word, but this is actually the popular word for this. In other words, it is a 0, half, 1 vector. Furthermore, a point is an extreme point if and only if. This is going to look very similar to things we did in the second case of Edmond's perfect matching polytope theorem. In fact, the proof is also very similar to that. Furthermore, X is an extreme point of the fractional perfect matching polytope if and only if the graph induced by the support of X, which is something we did in the proof, the subgraph induced by the support of X is a spanning subgraph whose each component is either an odd cycle or K2. Is a spanning, well, spanning is clear because it comes from the degree constraints, is a spanning subgraph whose each component is, in fact, I will just draw two components, K2, and I will draw an odd cycle. And in fact, you can go further and say what the values will be. If I tell you that each component is K2, well, K2 components just means that it has to be 1 over here. If the whole component is K2, then for the degree constraints to hold, this is the support. So there are no other edges here are part of the, they are all going to be 0. So that means this has to be 1. And in the case of odd cycle, it's fairly clear. If you do a bit of math, whatever that means, you will see that it has to be half everywhere. Let's do a quick example of the standard graph, right? So the triangular prism, if you consider the perfect matching polytope, how many extreme points does it have? The perfect matching polytope of the triangular prism? 4. Because there are 4 perfect matchings, right? So, if you consider the perfect matching polytope of C6 bar, it has 4 extreme points. However, if you consider the fractional perfect matching polytope of the same graph, it has how many extreme points? 4. Those 4 are definitely there, but there is one more. There are 5 extreme points. And the 5th extreme point is exactly what this theorem is talking about. Right? It's exactly half, 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 0 everywhere else. Okay, so that's one way to think about this theorem. It's saying that the fractional perfect matching polytope in general can be larger than the perfect matching polytope, but it still has some nice properties. It is, in particular, half integral. Yeah?
That's where the name fractional.
Sorry?
Fractional name comes from.
Yeah, that's a good point. Maybe the name fractional comes because of that, because you can have extreme points that are indeed fractional. Yeah, could be. Right. Okay. So we are going to assume this and prove the other direction, and we are also going to assume whatever else we want. Basically, this definition of Birkhoff on line. Well, once you prove it, it's also definition. We have very little time. Let's do it. Okay. So, which direction is done? If there is an odd conformal bicycle, then we are done with that direction. Okay. Now we prove the other direction. So now suppose that the graph is not Birkhoff on Neumann. Let's say G is not Birkhoff on Neumann. Yeah. If G is not Birkhoff on Neumann, we want to show that there is an odd conformal bicycle. Yeah. Well, if it is not Birkhoff on Neumann, it means that this set is non-empty, right? The perfect matching polytope is properly contained in the fractional perfect matching polytope. Yeah. But that also means that the fractional perfect matching polytope will have an extreme point that is not in the perfect matching polytope. Do you all agree? This is something we used earlier also, right? So not Birkhoff on Neumann means that the perfect matching polytope is properly contained in the fractional perfect matching polytope. If all the extreme points of this were here, then the whole fellow would be here because of convexity, right? So therefore, there has to be an extreme point of this fellow that is not here. Yeah? This implies that the fractional perfect matching polytope has an extreme point that is not in the perfect matching polytope. Yeah? That is something we already used when we proved Edmond's perfect matching polytope theorem. Is that correct? Okay? So there is an extreme point of this fellow, fractional perfect matching polytope, that is not in the polytope. But we know that all the extreme points, because of this theorem, which is a DIY, we know what they look like. They are half integral. They look nice. Just a bunch of odd cycles and a bunch of K2s. Or maybe just odd cycles, or maybe just K2s, right? Whatever. But of course, if it's just a bunch of K2s, well, then that's just a perfect matching. And then that actually lies here. So therefore, in any such extreme point, you have to have at least 2 odd cycles. The number of odd cycles will be even number because of matching covered graph. Right? So, this implies that extreme point x. This implies that the graph induced by x, by the support of x, has at least 2 odd cycles and it has an even number of odd cycles. Yeah? It has at least 2 odd cycles and an even number of odd cycles. And these are of course vertices joined. In fact, maybe I should write spell it out. Each component is K2 or an odd cycle. Yeah. So by Theorem 7.7. Each component of this graph is K2 or an odd cycle. Since this point X is not in the perfect matching polytope, we infer that the graph induced by X has at least two components that are odd cycles, and since the graph is matching covered, there has to be an even number of such components. Yeah? So you have a bunch of odd cycles, two or more, even number, and the rest of the components are K2s. Yeah? So your drawing looks like this. Let's just draw some odd cycles. Maybe I'll draw a different color. So I have some odd cycles, 1, 2, 3, 4 maybe, and I have a bunch of K2 components. This is what the graph induced by the support of X looks like. Yeah, maybe 4 and 4 is equal. That's not good. Make it 5. Okay. So this is my graph induced by the support of X. Yeah, everybody agrees? In particular, do you all agree that the set of odd cycles is conformal subgraph? Outside there's a perfect matching. Yeah, okay. So, yeah, so therefore the graph induced by X has a set of components, let me just call it, has a set of odd cycle components I'm referring to all the components, right? I'm referring to take all these odd cycle components. Let's say I call them Q1, Q2 up to QR, so that this entire subgraph is a conformal subgraph. So that Q1 union Q2 up to QR is a conformal subgraph. Yeah, you have a bunch of odd cycles. It's an even number of odd cycles. When I delete all of them, the remaining graph is a perfect matching. You all agree? This is what we have. If R is equal to 2, we are done. If R is equal to 2, we are done. So now the question is, if R is bigger than 2, can we bring it down to 2? If R equal to 2, done. Now suppose that R is at least 4. Yeah? Okay. Since we are running out of time, this is a good point to stop and make this a TIY. We'll finish this in the next lecture, but it's actually a good idea to try it yourself because now it just uses SGT. Okay, at this point it is all just SGT. So TIY using basic SGT stuff from module 5. Okay, and to be continued. Okay, are there any questions or concerns? All good? Alright, so we'll finish this proof next time, and then hopefully we all, including myself, will be motivated to prove Theorem 7.5. Thank you.